Hi everyone, we are Group 11 and our senior project focuses on developing a parking assistant application using IoT devices and machine learning on the edge. Our project advisor, Dmitry Zorpas. The motivation for our project stems from significant issue in urban areas, the search for parking spots. This search is responsible for up to 30% of traffic congestion, where drivers waste approximately 7.8 minutes in average for searching a free parking spot. Even though the traditional parking system rely on a sensor-based and manual method, they are often costly and inaccurate. So our solution is implementing power-constrained microcontroller-based system with machine learning on the edge for real-time parking slot detection that aims to save time and enhance the efficiency of smart city operations.
During our senior project, we focused on implementing a parking lot occupancy detection system. The system consists of battery-powered edge devices equipped with cameras that can potentially be installed in a parking lot. Each edge device in turn is deployed with a pre-trained convolutional neural network that can classify each parking slot as vacant or occupied. To achieve that, the image taken by the edge device is divided into many patches that each represent one parking slot. Each patch is then sequentially fed into the model, and the inference results can be accessed through a Telegram bot. Next slide, please. For the hardware, we use OpenNV and Raspberry Pi 4 as edge devices. As for the models, we use two CNN architectures introduced by Amata and Mohan, and then devised a smaller version of the M-AlexNet due to OpenNV strict memory constraints. Then, after training the models, we applied full integer quantization, converting the trained models from float 32 to integer 8 precision, which allowed us to deploy them on the edge device. And as for the dataset, we use publicly available CNR Park EXT dataset. To evaluate performance of the models, we built parking lot replica with toy cars.
Model was evaluated using 4 evaluation metrics. The first one is different camera angles. We took 2 camera angles which are straight and inclined. They are depicted in the screenshots here that are taken from the Raspberry Pi device. Here, occupied spots are depicted with green and the vacant spots with red patches. If the model is able to make good inference despite the camera angle, it proves its robustness to varying perspectives and its efficiency despite the camera angle. Next evaluation metric was weather conditions. We considered 2 cases, including snow coverage and puddles. In order to imitate that, we took white papers on parking lot to simulate snow coverage of the parking lot. Puddles were simulated by darkly colored small patches that were placed on individual parking slots. Considering different weather conditions proves the robustness of the system to diverse environmental settings and how it can be deployed in various geological conditions. Next evaluation metric is light intensity. Considering light intensity is important as it changes the visibility and the clarity of the input image and can affect the model accuracy. We consider 2 light intensities, which are normal and reduced. The normal light condition was equal to 100 lux, which is comparable with room lighting. Whereas reduced light condition was equal to from 5 to 50 lux, depending on the distance from the light source. Another evaluation metric was obstacles. Considering obstacles is important as a parking slot may be occupied not only with vehicles, but with other removable objects such as humans and animals. It imitates a realistic and a dynamic environment. In our case, we simulated non-vehicle objects with toys. The results of our evaluation process are demonstrated in this table. Here we can see 3 models and their accuracy and sizes on both devices. What can be observed is that a MalixNet with input size of 224 achieved the highest accuracy on Raspberry Pi device, which is reasonable as advanced CNN on a powerful edge device would produce good results. However, running the modified version of the same model with input size of 32 on OpenMV also produced sufficient results. Also, we can see that the MalixNet size is much smaller than Mohan's model. However, the results were comparable or even better. And this proves the diminishing return in accuracy with the increased model size. Coming to Mohan's model, we can see that OpenMV achieved higher accuracy compared to Raspberry Pi. And this proves that some models may perform better on more resource-constrained devices.
So moving to the next slide, and here you can see demonstration of our model in action. In this video, you will see that we place and set up our model on Raspberry Pi, put 2 cars, and you can see in the video how it changes. So occupy spot is detected as that there is a car, and according to that, the color of this rectangle is changed. So also we can demonstrate with obstacles that was introduced previous slides. Here you can see that these obstacles are not marked as occupied spots, and that confirms that our model is accurately distinguished between cars and non-parking objects. And on next slide, you can see the small test on real parking, where one car is unparking from this place and going to and driving away. Those squares are pre-selected before putting this OpenMV camera microcontroller. And moving to the future.
When it comes to future work, one of the ways to improve our project is by improving its evaluation metrics. For this senior project, toy car simulation environment was used. Of course, it is more advisable to validate our results on real parking settings by setting the device in one of the real parking lots and by using the user interface to see if it works well throughout the period. And also try out the device in parking lot with different weather conditions. And another way to improve our project is by incorporating dynamic detection. It can be done first by considering different architectures that can dynamically detect car vacancy and then implement and train them on a memory-constrained edge device. In conclusion, parking occupancy classification can be done with memory-constrained edge devices with lightweight models. Inefficient urban parking, which was the main motivation for our project, can be tackled through CNN models operating on the edge. Moreover, computational power of memory-constrained edge devices such as OpenMV can be sufficient for car occupancy classification. And as it was stated in the results section, the performance of lighter models on a more constrained device was reasonably comparable to the performance of bigger models. Here you can see our reference list. Thank you for your attention, and special thanks to our advisor in IoT Lab.